let's do a K-map example problem. So here's the question. Let's simplify an expression. Let's simplify xy plus x inverted and y, or x inverted and y inverted. So this Boolean expression is x and y, or inverted x and y, or inverted x inverted y. Let's simplify this using a K-map. There are other ways of simplifying this. We could use Boolean expressions to simplify this. Now, if I look at this question, I will see that there are two variables. So I see there's x, there's y, and sure, x can be inverted and y can be inverted, but this, so solution, first I identify that this is a two variable question. So I'm going to make a two variable K-map. To make a K-map, I want to have spaces for all of the combinations of variables. I want to have a space for x. I want to have a space for x inverted. I want to have a space for y. And I want to have a space for y inverted. And I did not have to start with x here, and I did not have to start with y here. I could have started with the inverted, but what's important is that we use grayscale. And grayscale means that we change one digit at a time. So here I went from y to y inverted, and I only I only changed the y. Now, this is a difficult example because it's only two variable. On further examples on the next video, I'll show you that what I mean about only changing one variable. But this is grayscale. Grayscale just means change one digit at a time. All right, now I've made my little K-map grid. It's going to hold all of the possible variables. And now I need to look at my question here as the next step and say, well, where is the union of x variables and y variables? Where do they exist? Where do they equal 1? So up here, I see that the union of, the term x and y exists in this equation. So I'm going to find where x is. So here's x, here's y, and where they both are ANDed together, I'm going to put a 1 here. So it's a little bit of a fun process to fill this in. Let's look at the next, the next term has two factors. It has an inverted x, and it has a y that is not inverted. And so if I go down and over and see where the union of those two factors are, I get this term that is represented in the Boolean expression that I want to simplify. And lastly, the last term in this expression has two factors. It has the inverted x factor and it has the inverted y factor. Here we go. And the union of those exists here. Now, there are a couple of rules to what we do next in the K-map method, and we can simplify those rules. This is what we do. We basically, first we made map, right? We made this map, and then second, we put ones in the terms from the expression. And then the third step is to do some looping. Third step is going to do some looping. All right, so the third step just does looping, and here's the way to do looping. Let's just simplify this. You have to loop the ones that are by themselves. Loop lonesome ones. All right, loop some lonesome ones. And then you're going to loop as big as possible. You know, eight ones would be really big. You can loop 8 ones if you can see them. Loop 4 ones, loop 2 ones. All right, so it's basically 2 to the n combinations of 1 you can loop. But wait, there's more. Yes, you can overlap. And yes, you can go off the sides around to the other side. This is not a video about why this is true. This is a video about how to use the Karnaugh Map method. Why it's true is you'd have to look at kind of the third dimension of how this is laid out, and then you can figure out that you can loop over to the other side, because really this is like a surface that all touches. But anyway, we're going to do looping. We're going to look for some lonesome ones, make sure they get looped separate. I don't see any lonesome ones. They're all sitting here beside a partner. Then I'm going to loop as big as possible. Do I have a loop of 8 ones? No. Do I have a loop of 4 ones? No. Do I have a loop of 2 ones? Absolutely. Look at that. 2 ones sitting together there. That makes me happy. I can do that loop. But then wait a second. But wait, there's more. You can overlap. Ooh, then I get to get these 2 ones as well. That's pretty neat. Wait a second. Yes, you can go off the sides around to the other side. Do I want to do that? Well, sure, I could. Here's an example of that. I could go off this side and onto this side. Cool. I'm allowed to do that. That's perfectly valid. Why would I want to do that though? Because I'm just looping those same ones that I already looped. All right, let me show you that again. I can go and I can loop this one off the side with this one. There's another loop. Do I want to do that though? No, because I already looped those 2 ones, so there's really no point of it. But that's what I mean by going off the grid and over to the other side. Okay, so I loop these. Now my next step, I can do in another color here. Actually, I have to put the steps in blue. So my next step here is to find what's common in each loop. Let me write that a little bit more from first principles. Actually, I'll just say find what is common in each loop. And then I'll put here in like, you know, gray, I'll say because the union of those groups simplifies to what is common. The union of each group simplifies to what is common. All right, that's like why we do it. Okay, so next color for that then. So I'm going to look at each group. I'm going to look at this group and I'm going to say, okay, find what is common in this group. What is common? Y is not common. Y is not common. Y bar is not common because both of these ones, this one and this one, do not have Y. Only one of them has Y. They don't have Y bar. Only one of them has Y bar, right? Y inverted. Okay, so let me just erase those for clarity. So they don't have those. But in this loop, let's see. Do they both have X? No, none of these ones in this loop, none of these have X. No. Do they both have X inverted? Well, this one has x inverted, and this one has x inverted. So I would say that x inverted is common in this loop. X inverted is common in this loop. Let me just clean up my drawing here a little bit. Yes, X inverted is common in this loop. Okay, let's do the other one then, because I have to find what's common in both loops. And so this is the other loop. X is not common because one of these has X, the other one has X inverted. Y looks like it's common. It looks like this one has a y factor in its term. This one has a y factor in its term, right? It has a y factor. They both have y factor. So I would say y is common in this group. All right, y is common in this group. Clean it up a little bit. All right, then last step in the K-map method is to just do a therefore statement and say what the answer is. 5, state the answer as sum of products. Now, that's again silly. It's not going through first principles. Why is that the answer? Because if you look at the union of all of these things, then what they would simplify to would be therefore the simplified Boolean expression is sum of products y or inverted x. You know what? That should be done in alphabetical order. It is inverted x or y. Okay, you could also put it like this. Therefore, x, y, or x inverted and y, or x inverted y inverted is equal to x inverted or y. And you can use your Boolean expressions to confirm that that's true. But this is the answer because the union of all of these things would actually simplify down to just that. And that's an example of how we use the K-map method, not necessarily why the K-map method works this way, but that's how you use the K-map method.